returned. Project 3 is still going to be being graded, which is the Bayes networks, and there will be at least one more project. I will hopefully give it to you by next week. It's most likely going to be on the learning part. Okay. So the other things are that the TA sent a mail. Bill Cushing sent a mail to you guys about the fact that there will be a recitation session tomorrow, right? Right at 12 to 1, right after his office hours, because we're going to have the test on Thursday. And if this is very surprising to you, then you're missing some models of the world. So that's, I guess some people wanted a recitation session. It's optional. You don't need to go, but if you want, then you have to pick a time. Yes?
Will you repeat the time, please?
12 to 1, I believe. He sent an email. It's probably on the mail archive here. Yeah. Okay, there. Can you see? Burning BY, so BYLG210, which is half a floor above, from 12 to 1 tomorrow. Okay, tomorrow being Wednesday. And I think 11 to 12 is his office hours anyway. Okay, so that's something that he mentioned. I mean, he had to pick a time because there is any specific time, there will be some people available, some not, and so he picked that. Okay, that's the situation regarding that. And then, the test would be on Thursday, and it would be, as I said, the planning graphs, everything that's been done after the last midterm, which basically we didn't cover planning graphs there. So planning graphs, propositional logic, satisfiability, as well as propositional theorem proving, okay, and then Bayes networks and inference on the Bayes networks, but not the learning part of the Bayes networks, okay. So that's what it's going to be. So it's mostly the homework that you just got done. Okay. And then I posted the solutions for that. Some of you pointed out that one of the HTML files had funny characters. That's just incompatibility issues. Those funny characters don't have any secret messages. Just ignore those funny characters and you'll still get the answer. Okay. That's where we are. Any questions? Okay, so then what I am planning to do right now is basically continue with the topic that we're going to be discussing today is generalized learning. So we sort of looked at learning. We were in Bayes networks and we started learning about Bayes. So we started learning the parameters and structure of the Bayes networks from data. Okay, so in fact, you must be thinking, if you were thinking about this, you could have said, well, you did logic, basically propositional logic. So the idea for propositional logic was you could have written the domain model, the model of the world in propositional logic. Okay, and then the question is how to do inference with it. Okay, and then from there you went to Bayes, probabilistic logic, right, where you wrote the model of the world in probabilistic logical form, so Bayes networks. And then we talked about how to do inference, right? So we talked about inference here, we talked about inference here. Now, but as a little bonus, we also talked about learning here. Okay, that means if the expert didn't give you the model directly, you may want to learn it. And the way the expert, so the assumption here as well as the first part of probabilistic logic was everything is given to you. The model is specified by the expert and you only need to do inference. And then the second part of the probabilistic, the Bayes networks, we said maybe they won't specify the model, or at least they won't specify the full model. Maybe they'll just provide the structure and you learn the parameters. We started from there. Then we said, what if they provide the structure, but they don't provide the training data on some of the variables? Those are the hidden variables. Then we talked about expectation maximization last class. Then we also talked about what if they don't even provide the topology, the structure. Then we also talked about how to learn. Basically, you consider different structures and then find the best one, and then for which you find the parameterization. Okay, so we did this for the probabilistic logic. Now the question is, what about this guy? Why couldn't he have learned logical models? Do you see what I'm saying? There should be a symmetry in life. I mean, if this guy gets to have learning, this guy also should have a learning. Okay, so any model which could have been specified by experts should also be possible to learn. Okay, so the learning aspect that we looked at from the context of Bayes networks, that problem is not just special to Bayes networks. You could do learning with logical models. You could do learning with respect to probabilistic models. You could do learning with respect to numerical models, and so on. Okay, so what I'm doing today and one more class is sort of look at learning from a general perspective. And of course, again, every topic we do here could have been a whole course. Okay, so learning as a whole, there's like a graduate level course that's offered separately. But what we'll be looking at is to get some understanding of what are the fundamental issues in at least one particular type of learning problem called classification problem that we looked at earlier. Okay, and then talk about, so first understand the trade-offs, the kinds of issues you should be aware of in learning, and then of course actually go and at least teach you one more algorithm. So if I told you a whole bunch of learning algorithms for a probabilistic logic, right? I told you how to do parameter learning, I told you how to do EM, well actually I at least explained to you how EM works, and then I told you how the topology could also be learned. Right? So I would at least give you one example for logical learning, which is basically decision tree learning. A decision tree really is just a logical formula, a big logical formula. So from data, instead of learning a Bayes network, from the same data, you learn a logical formula. And since you can learn two different things from the same data, there's always this question of which is better. So how do you decide which learning is better? Okay? That's the first part of today's class, to understand what are the issues in learning from data. Okay, so that's basically what we're going to be doing today and a class after the test. Okay, so back to the example that we looked at. Okay, this is one type of learning. As I mentioned, in fact, in the Bayes network learning, I talked about learning the entire data versus learning just a part of the a specific subset of the variables, right? And when you, for example, when you think a certain set of variables are important, then that might be a classification problem. So in this particular case, there are a whole bunch of variables. All these are variables, but then there is one specific variable that you are particularly interested in. Each value you want to predict. Okay, it's normally it's called a classification learning problem. Okay, so the idea is I'm getting data which is defined in terms of the attributes and their values, and for each of these particular examples, you know what the class is. And what I want to do is, given new examples, I should be able to predict what their class would be. You see what I'm saying? Can somebody tell me, just to make sure that I'm not just talking to the walls, can somebody tell me why classification learning is a special case of Bayes network, the data learning, which is completely predicting the data?
Predicting only one column.
Exactly. So the idea is you'll only be predicting this. Okay? If I give you a test case where I know this column, but I don't know this, and I know this column, it won't be able to complete the rest for you. It's not like the Excel spreadsheet where, if you have a bunch of, well, actually even Excel spreadsheet doesn't work. Excel spreadsheet tends to be directional. So if you put a number in this column and number in this column, and this column is actually a function of these two columns, then it will put a number there. Right? So for example, your homework cumulative, your test cumulative, and your what else is left? Project cumulative. and then I say the total in the finals, the total course cumulative, which would be sum of these 3 columns. If I put numbers here, it will put a number there. But on the other hand, if I put one number here, and put a number in the final column, Excel doesn't necessarily fix this, even though you know what that should be. Do you see what I'm saying? Okay, a data learner would be able to fix pretty much any part. It actually essentially can predict any of the attributes of the data. A classifier focuses on some subset of the variables of interest, and only that it tries to predict. Okay, fine. So it's just a special case. Okay, so we looked at this last week, right? And then we used this. We learned a Bayes network for this data. In particular, we learned naive Bayes network for this data, because to get a real Bayes network, somebody either needs to give you topology or you need to search over topologies. Instead, you just went with the naive Bayes network, and then I told you how the parameters can be learned. Right? So because once you have a naive Bayes model, you know the model of the topology of the network. Given the topology of the network and given the complete data, finding the parameters is child's play. Calling it a learning algorithm, sounds kind of silly, right? So naive Bayes classifiers are extremely easy to write. Okay. Now, that's one way of learning from this data, so that you can predict the class of a new example, right? That's not the only way, it turns out. Here, at least, are some other ways of learning the patterns in the data. One way of thinking about this is a naive Bayes classifier is sort of trying to find some probabilistic patterns between the connections between the attributes and the class variable, right? And then uses that to predict the class of the test data in the future. Okay, but here is a different thing called decision tree learner. Decision tree learner basically it's a 20 questions learner. What it does is, given a new example, it asks a series of questions. So in this particular case, so this is naive Bayes classifier. It says Russell weights will cause all these other attributes, and it learns a prior for this, and it learns the CPTs for each of these. Right? That's what we learn. We know how to do this. Okay? There is another thing which we will talk about, either today's class towards the end or next class, hopefully today's class towards the end, which is a decision tree, where you're essentially going to ask a series of questions, saying, okay, let me look at in the current example, in the new example, what's the value of the patterns attribute? If it is none, then I'll just go ahead and say, no, he won't wait. Okay? If it is some, I will say he will wait. If it is full, then it's not clear. I'll ask one more question to decide whether he'll wait or not. This is my pattern. You understand what I'm saying? Okay? You can start thinking about how could I learn this structure from this. It's not that hard. For example, you might see that when patterns is none, its patterns is none here and none here, right? In both those cases, he wound up not waiting. So maybe that's what you keyed on. Your algorithm keyed on. Okay, so a decision tree learner learns a pattern like this. Now, what is this decision tree learner? It's actually, you can see that if these were, in this particular case, some of these attributes are non-Boolean. They are multi-valued. Okay, but for a minute, assume all the attributes are Boolean. Then what would a decision tree learner be representing? It represents an arbitrary Boolean formula. It represents an arbitrary Boolean formula in the following sense. Suppose, basically, you're looking at something like this. You'll ask, let's say, A, true this side, false this side. If then on the true side, maybe I'll ask B, true, false. Then here I'll ask C, true, false, and so on. And then here, yes, let's say. Then what I'm saying is A and B and C means true. Okay? And then similarly, A and if B is false, then I typically, let's say I ask D. And if D is false, then I'll again say yes. Then basically what I'm saying is, I'll say yes if A and B and C are true. I'll also say yes if A is true, B is false, and D is false. So a decision tree is nothing but a big disjunction of conjunctions. Disjunction of conjunctions. Now, try to put yourself back several weeks back, which is actually important because that's what the test is going to be partly on. We talked about canonical forms for propositional logical formulas. We talked about at least two forms, CNF and DNF. CNF is what we used earlier, which was conjunction of disjunctions. This is the other form, disjunction of conjunctions. They're both canonical forms in the sense that they're all normal forms. They're not actually canonical. They're normal forms in the sense any arbitrary propositional logic formula can be written either into this form or this form. Which is another way of saying, if there is a pattern in this data, that can be written as a big logical formula. There would be a decision tree corresponding to that formula. And you would learn it. The decision tree learner would learn it. Okay, and I'll tell you how such a decision tree can be learned. Now that you can find decision trees in this pattern, in this data, naive Bayes classifier in this data, before you only had one, so yeah, okay, whatever we learned. Now you have two ways of learning. Now the question is, which is better? Should you be looking for decision trees in the data or naive Bayes classifiers in the data? Okay, data never comes with a little, badge on its face saying, I'm a naive Bayes kind of a data, or I'm a decision tree kind of a data. So we need to understand, what are the trade-offs here? And that's not the only thing. In fact, depending on how we go, another way of looking at this learning is the following. So here you consider the data essentially from the point of view of a Bayes network generating the data. These are the samples from a Bayes network. You learned naive Bayes classifier. You learned it also as samples from a logical formula, and you learned the decision tree. I can tell you a different way of looking at it, which is the following. Suppose, and I'll write it, suppose I actually have data which is only two columns, that means two attributes, A, B, and the class. Okay, and if A is 4, B is 7, the class is yes. A is 9, B is 20, the class is no. A is 32 and B is 49, the class is yes. Data like this. Right? Now the interesting thing is, each of these are the coordinates of a, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is 10-dimensional data. Each data point really can be seen as a 10-dimensional vector. It's a point in 10-dimensional space. Okay? So if you can visualize 10-dimensional space, in this 10-dimensional space, there are 12 points in the 10-dimensional space. Okay? Some of them have plus written on them because they are the examples of the concept. Some of them have minus written on them. That's because they are not examples of the concept. What I'm really trying to figure out is what are, given a new piece of data, is it going to be plus or minus? Since it's, since many of you are probably not extremely good at visualizing 10-dimensional space, okay, let's think of 2-dimensional space. So here is my 2-dimensional space, and there. Suppose those are the points. How would you learn to classify a new guy? I got a new guy here. That's a new guy. Is the new guy going to be positive or negative? You all think it's negative. Why? There are many different ways of thinking about it. One, of course, is you may be thinking in your head that there is some kind of a plane separating positives from negatives. And what I really need to learn from this data is the equation of this plane. It's a hyperplane. In two-dimensional space, hyperplanes are straight lines. In three-dimensional space, hyperplanes are what you and I call normal planes. In four-dimensional space, hyperplanes are three-dimensional spaces. Okay, so you can't quite see it. Okay, so don't try to because you will hurt your head. But all I need, but from a mathematical point of view, the plane's equation is easy, right? So if I give you a straight line equation, above that is positive, below that is negative. If I tell you that, then I give you a new point. I plug that into that straight line equation and see if it is above or below. And if it's above, it's positive. If it's below, it's negative. If I do that, then essentially I'm learning it in a different way, which is I'm learning a decision surface that separates positives from negatives. That's a third way of learning. That's a third way of learning. Okay? The problem is the same. I'm still interested, for some crazy reason, I'm still interested in predicting, in my case, whether Russell will wait for the restaurant or not. But as I said, this is just symptomatic. This is one example. Another example would have been a particular credit card transaction. Okay, and the features of it. Is it done from the same country as the cardholder's country? Okay, is it done in the morning or in the night? Is it for more than $1,000 or less than $1,000? Has there been many transactions in the past 3 minutes on the same credit card? These are all features. And then for each of these, you may have some training examples, that is you, the Citibank or JP Morgan, has some training examples saying, for some of these examples, we found out in the end that this was a fraudulent transaction, this is not a fraudulent transaction. Based on that, we want to learn the pattern as to what is a fraudulent transaction, what's not a fraudulent transaction. Okay? Is that problem any different from this? No. Okay, so that could be. And similarly, it could be spam mail versus non-spam mail. A bunch of features of the mail, who is it sent from, etc., etc. And based on that, was it seen by the user to be spam or not? And from bunch of training examples, you want to learn to classify newly arriving mail as spam or non-spam. And if it is spam, then you put it in the spam bucket so that the user won't be inconvenienced by having to look at it. Right? So they're all the same classification problem. And for each of these problems, I could have done either naive-Bayes, or decision trees, or decision surfaces. Okay? So it's like I'm looking for different kinds of patterns in the data. In this case, I'm looking for decision surfaces. In this case, I'm looking for Bayes networks. In this case, I'm looking for decision trees. And as they say, look and ye shall find. Right? If you look for decision trees, you will find decision trees. If you look for decision surfaces, you will find decision surfaces. If you look for Bayes networks, you will find Bayes networks. The question is, what should you look for? Okay, that's the general problem that we are interested in learning. Okay, and furthermore, each of these can be drilled down. It turns out that I could have a decision tree which is only 3 levels long, 3 levels deep, and classifies the data reasonably well. Or one which is 38 levels deep, and classifies the data even better. Or yet another one which is 100 levels deep. Of course, remember that it can't be more than the number of attributes, right? Okay. If you have more than a number of attributes, that means you forgot some of the answers that the guy gave. It's just going into cycles. Okay, so you will have 100 levels deep. Which one should I pick? Here, I just went into naive Bayes because I just wanted to get done fast. But we knew that a better thing is to consider different topologies, and then find for each of the topologies what's the best parameterization, and compare those topologies in terms of the likelihood they provide to the data and pick the winner. That would have given you decision tree Bayes networks that are not naive. That could be deep Bayes networks. I could have been even more eager in looking for patterns, wherein not only would I actually consider deeper Bayes networks, but I will make up additional attributes which don't exist anywhere and throw them into the network. Have I done this? Please say I did it. Okay, the answer is yes, I did. Because that's what EM was all about. We made up hidden variables. Okay, so in fact, you can have hidden variables and unknown structure. And so you can have lots and lots of fun. That is, structured learning with incomplete data. Which one should I be doing given this data? Okay, now, furthermore, in fact, this point will be made much, much clearer, even here, for example. So I have, in the decision surfaces case, I should probably put different color. Okay, that's how my examples look. Well, I could do this as my decision surface. Okay, that's a straight line. Okay, but I could also do something like this as my decision surface. Let me put it in green. It doesn't look like a surface, it looks crinkly. But man, that's much better with the training data. Which one is better? I want you to think that finding this kind of a surface is like finding a deeper network or finding a deeper decision tree. Sometimes it's the right thing to do, sometimes it's the wrong thing to do. What you would hopefully learn today is when is it likely to be right thing to do, when is it likely to be wrong thing to do. But you actually know a little about it already from last week's discussion. The question is, should I go with this guy or this guy? And in some sense, think of this as one hypothesis, H2, and this is H1, hypothesis H1 and H2. And it depends on what do you think is the prior probability of this hypothesis before seeing the data. Do you think the data is linearly separable, in which case you should probably find a line? Or do you think it's likely to be a 7th order polynomial surface? In which case you probably should look for this. Typically most people, remember the prior of the hypothesis in the Bayesian learning? Okay, that prior would essentially tell you whether all hypotheses are equally created or not. And in some sense, most people, I don't know about you, but most people think this is good enough learning. This is overdoing it. In fact, they would say the word for overdoing, the colloquial word overdoing, has a technical word in learning called overfitting. You're overfitting to the data. And you think whenever you overfit to the data, it's not a good learner. Okay? Now, first of all, it's interesting. Finding lines, there are fewer lines. Although there are infinite number of lines, there are still fewer lines than there are 7th order polynomials, because 7th order polynomials include as subcase 6th and 5th and 4th and 2nd and 1st order polynomials. And 1st order polynomials happen to be lines. Right? So if you're searching between all funny looking hypotheses, this is a much bigger space than just the ones for lines. Similarly, if you're looking for the best naive Bayes classifier that lives in this data, that's a cheaper search than the best Bayes network with only these attributes that lives in this data, which is still a cheaper search than finding a Bayes network that has these attributes plus some more hidden attributes. And the same thing here. The short decision trees are easier to find than larger ones because there are fewer decision trees of only depth up to 3 than there are decision trees of depth up to 15. And you need to somehow compare them to see how they fit the data. So these are the issues that we want to understand. So given that there are all learning methods for this, learning methods for this, learning method for this, and you certainly know what did we do here? You certainly know the learning method for this, and you will hear about this as well as this before you're done. But today I want to first understand, what are they? How do we decide between them? And even within each of the class, how eager do you want to be in classifying the data correctly? Okay? So that's the problem that we're looking at. It's called the inductive learning or classification learning or supervised learning problem, supervised classification learning problem. So the abstract specification of the problem is given a set of labeled examples where the examples are defined in terms of a set of features and their values, set of attributes and their values. And then each of these examples is given a class. The simplest classification problem, Boolean classification problem. It's true or false. You can also do multi-class classifications. Okay, so if I don't say anything else, let's assume we're just doing Boolean classification. Okay, so basically I want to, given a set of labeled examples and a space of hypotheses, you need to tell me what kinds of hypotheses are you looking for? Bayes networks? And if so, naive Bayes or full set, decision trees or decision surfaces. Then you have a set of hypotheses. Then you're trying to find among this set the best hypothesis that fits the data. Okay? And how do you do this? Well, the idea is simple. You have the set of hypotheses. Let's act as if just finite set for a minute. So you write a big loop. Okay? And pick the first hypothesis, compute how well it fits the data. And then give a rank to it based on its fit. Next hypothesis, give a rank to it. Next hypothesis, give a rank to it. And then pick the data which has the highest fit. Okay? That's it. That's all. That's learning. Okay, it looks almost dumb, right? Basically, you just run through all the hypotheses. Now you might say, well, what happens if the hypothesis space is not discrete but continuous? I have infinite set of hypotheses. Well, you did it last week. Basically, you computed the likelihood of the data as a function of the parameters of the Bayes network, and you maximize the likelihood. So you just did, calculus, basically. You found the derivative, equated to 0, and found the maximum likelihood. So in that case, essentially, the likelihood of the data was being used as the fit to the data, which is a reasonable thing. How likely would this data have been if this was the hypothesis? Okay. Now, so if you don't have continuous, we already looked at continuous, but let's look at discrete for a minute. Would discrete be any easier? Well, if you are assuming that there are, if you are assuming that there are n Boolean features that define each of the examples, then the question is you're trying to find out what is the Boolean function that tells you whether an example has class true or class false. That means I just need to find out how many Boolean functions are there on n variables. Right? How many Boolean functions are there on n variables? If you have n variables, you have n columns. Okay? N columns. That means there are 2 power n rows. And this is the class. You can put true, false in any which way in this column. That would be a function. How many different ways can you put true, false in 2 power n cells?
2 power
2 power n different ways. So if you have just 6 attributes, okay, then there are these many possible Boolean functions. That's 2 power 6. So even if you have a very fast computer, it's going to take a while to go through each of the hypotheses and find the optimal hypothesis. Okay? So in general, we basically probably are not going to do this as an optimization problem, true optimization problem. We might want to be greedy. In the case of decision trees, we'll actually look for a greedy algorithm. But before we go to greedy algorithms, remember that computer scientists are supposed to first understand how hard is the problem before they find the cheap solution. So part of what I want to do is, how do we talk about complexity of learning? You know about complexity of problems, right? I mean, worst case complexity of running, sorting algorithm, worst case complexity of learning, a graph search, worst case complexity of doing inference in propositional logic, and so on. How do I talk about complexity of learning algorithms? That's another point that I want to understand. Okay? Continuing along. Stop me if you have questions, by the way. I'm basically making you think about the issues in learning and some answers, and then we'll go to decision trees. Okay. So I want to loop through the hypothesis and then pick the hypothesis that's the best, right? And then I also want, in doing this, I already realized that probably I won't mind doing a greedy approach. May not be picking the best hypothesis, maybe picking a reasonable hypothesis. Okay? But I still need to know how to compare 2 hypotheses, at least. Right? In the probabilistic case, we sort of compare 2 hypotheses by looking at the likelihood they provided to the data. But let's look at it in a slightly more general way and say that I would say that a good hypothesis will have the fewest false positives and the fewest false negatives. Okay? If it's a Boolean classification problem, then hypothesis is good if it basically, for a data which is actually positive example, it says positive example. And for a data that's negative example, it says negative example. Okay, if it makes mistakes, then the mistakes are counted. Now, one point I want to say is the mistakes can be asymmetric in terms of their cost. Do you understand what I'm saying? A false positive is done when you take an example that is actually negative and say it is positive. False negative is done when you take an example that is actually negative and say it is positive. I'm sorry. False negative is done when you take an example that is actually positive and say it is negative. So you falsely accuse it of being negative. Okay? Now, if all errors are created equal, false positives and false negatives each give you one unit penalty. But depending upon your learning scenario, false positives and false negatives can have completely different costs. You want to understand that, right? So for example, if you have spam mailer, which is more costly, false positives or false negatives? So I'm trying to judge whether a mail is spam mail or not. Okay? The program. And if I decide it's a spam mail, I'll put it in the spam folder. Should I be minimizing my false positives or false negatives? I mean, which should be more costly?
False negatives.
False negatives. In the sense what? It's not a spam mail. It's Rav saying, by the way, test on Thursday will actually have extra questions. And you say, who is this Rav? It's coming from Nigeria or something. Let's put it in spam mail. And that's a false negative, and you're going to pay for it. Okay? How about credit card transactions, fraudulent credit card transactions? Is false positives and false, notice that, it's not that I'm saying in the case of spam, all you care about is negatives, not positives. I'm just saying if you have one false positive, one false negative, then a false negative has slightly higher weight than the false positive. right? How about credit card transactions? Which one is fraudulent versus is not fraudulent? Which would you rather prefer? What is costly? So if you say, if it says, so again, positive means fraudulent, negative means not fraudulent. Okay? If you consider a non-fraudulent transaction to be fraudulent transaction, they will just, what will the credit card would do? They'll just basically reject the transaction, call you on the phone, and see, did you really authorize it? If on the other hand, if it is actually a fraudulent transaction and they think, no, I'm sure Rao just is buying, a Lamborghini, today, right after dinner, fries and a Lamborghini, from McDonald's, right? Then essentially you won't call Rao, you won't waste his time, but then you're going to take a huge, big hit. So credit card transaction people do actually have a slightly higher cost to false negatives than false positives. They don't mind saying more transactions are fraudulent because that only means they have to call you. Do you see what I'm saying? So I'm just trying to make you think that in trying to figure out how to compare two hypotheses, the simplest idea is to say how many examples is this hypothesis fitting correctly. And the one that fits more examples correctly is better than the one that fits fewer examples correctly. But then sometimes the errors can be having weights. False positive errors can be higher weight than false negative or vice versa. In general, the rank of a hypothesis is some arbitrary function of the number of false positives and some number of false negatives. If it is, the simplest case is just add them up. Okay? But sometimes it could be weighted. Sometimes it could be square of this plus cube of this. Whatever you feel like. And these are essentially called the loss functions. Each hypothesis is losing in classifying the data. The one that you want to pick is the hypothesis that has the least loss, or the most fit. Looks good, right? Now comes the central question. On what data are you going to decide the fit of the hypothesis? Training or testing?
Testing.
What would you rather do? If you are the God, okay, and you can either ask me for Thursday's exam and prepare for that, or just work on the homeworks and prepare for that, which would you rather pick? The test. The test. Do I need to tell you this, really? I mean, some of you really are in this course to learn the material. I'm so impressed. But, most of you probably want a grade. And so you really want the test. You want to be correct on the test. Learning is about future, not about past. By the way, one beautiful point that may be worth understanding is learning and compression are highly connected. Okay, if I have a whole bunch of positives, whole bunch of negatives, and if I just find an equation for a line that separates them, that equation takes much less space to remember than all the examples. So I compress the heck out of the data. Right? When I compress the data, then that equation also allows me to predict future. If you're only interested in compression, then all that matters is, do you have lossy compression or lossless compression? Okay? So it's clear that this is a lossless compression of this data and this is a lossy compression of this data. Okay? The question then is, what about learning? While compression is part of learning, learning is really about future, not about past. So what you really want to do is to reduce your error on the test data, which unfortunately I haven't given it to you. Okay? So you are reducing your error on the training data, not because that's what you wanted to reduce your error on, That's because that's the only one you have. This is again the classic case of drunk searching for his keys under the lamppost. Not because they lost the keys under the lamppost, but because there is light there. Okay? You do basically try to reduce the error on the training data because you think that doing that hopefully will also reduce the error on the test data. This actually means a bunch of things. It first means that you somehow believe that the test data will be coming from the same distribution as the training data. What is the way I can make you unhappy about Thursday's test? Here is one I just thought of. Right? Which is the entire test will be about proofs of complexity of NP completeness from sense exams. I don't have time. I don't feel like setting up a new test. I'll just give all problems from sense course because he already has a test. I'll just give it to you. Is that a reasonable test? It's a test, all right. Okay. It's not reasonable because I showed you some examples on which you can train yourself, and then you don't see a thing about it in the test. But that's not the only way I can make the test unreasonable. I can make the entire test on Thursday be just about planning graphs. The entire test just about planning graphs. I'm giving you hints. Okay? Right? Okay. Would you consider that to be a fair test? No, because you only did one problem on planning graphs in the entire homework. So you sort of assume that 1 out of 5, 6 problems will be a planning graph problem. And yet, the test, all 10 or 28 problems that I'm going to put in will be about planning graphs. It's not the length of the test that really makes you unhappy. At least that's what I hope. It is whether the distribution of the test is similar to the distribution of the training data. Okay? We all have highly, deeply held belief about what is the unfair test versus fair test. I had this story I tell every time I mention this. My wife, when she took a course in theory of computing, the teacher, in that particular case, did NP completeness in the last class, just one class. And the entire final was an NP completeness proofs. Entire final. So obviously, she did not get her A+ in that test. So what's interesting about it is, 20 years later, she met another student who took the same exact test, going up in an elevator in some random place. After saying hello to each other, the first thing they said is, "Can you remember that crazy test?" 20 years later, they remembered how unfair that test was. It's true that she's a faculty member, and so she probably doesn't have that much of a life, but, and so is the other person. They were both faculty members. But in general, we have this feel for what is a fair test versus unfair test. And a fair test hopefully comes from the same distribution as the training examples. So that's the assumption you are making about the future for the learning to be satisfied. You can always make the learning fail by just giving for giving training data that's not representative of the test data. So if there is a whole bunch of problems in AI, I'm using some random distribution to pick the homework problems, I better use the same distribution to pick the test problems. Otherwise, you're going to yell at me. You'll yell at me anyway, but you'll yell at me 20 years later too if I use a different distribution. Okay, that's one point you're making. The other point is this. When you are studying for the test, are you trying to increase your fit to the homework solutions that Rao provided? Or are you trying to do well on the test? In particular, if I have, in this example, these are positives, these are negatives, would you go for this as the hypothesis or this as the hypothesis? Why? because you think teachers can make mistakes. Surprisingly, teachers are human. And your training data can either come from a teacher or from nature, and there can be noise. And by overfitting yourself to the data, training data, you're likely to make more errors in the test data. So, for example, if people as part of the answer for the Bayes network question that is surely going to be there in the test, put a whole bunch of symbols like this, I know you overfit because those symbols are showing up as bad HTML characters when you looked at the homework. So you sort of assume that must be part of what is involved in doing this. So let me put a whole bunch of those. I'll at least get partial credit, for the funny question. You see what I'm saying? Okay? So this is a technical point. It's not a made-up point. If you were to, for example, consider a whole bunch of hypotheses. These are the hypotheses. Okay? And with respect to these hypotheses, these are organized such that these are straight lines, and these are first order, second order, third order, 15th order, 19th order polynomials. So as you go like this, you'll get to overfit to the data more and more. And with respect to each of these hypotheses, the straight lines obviously are going to make an error at least. One negative and one positive would be misclassified because there is no way of linearly separating this data unless you have a different conception of lines than I do, right? So straight line data, some hypotheses are likely to have pretty high error on the training data. As you keep going, the error on the training data reduces. It's clear that you should look at the homework solutions. It's true that the teachers can be wrong, but it's not, I'm not saying they're always wrong, 100% of the time. So you should look at the homework solutions. So if you don't look at the homework solutions, a guy who doesn't look at homework solutions at all and comes to the test is likely to do badly on the test. The guy who looks at the homework solutions so much that they have sort of, imprinted, burned them into their brain are also likely to do badly because they're going to reproduce my errors rather than understand the material. Okay? So the interesting thing that means is as the error of the hypothesis with respect to the training data keeps reducing, the error with respect to the test data first reduces and then starts increasing. I want you to understand this. This is what they mean when they say you overfit the data. When you overfit the data, you reduced the error of the hypothesis with respect to the data all the way to zero. But unfortunately, there is noise in the data, training data. So in trying to, you basically fit yourself even to the noise in the training data, just like my question marks in the Bayes network example. And so then, if you use that hypothesis, you're likely to do worse on the test data. Because the noise doesn't have to be the same next time around. This picture, by the way, is called the bias variance trade-off. Okay? The idea is, finding lines means you have strong bias for finding lines. Finding second order polynomials is weaker because it allows both lines and parabolas. Finding third order polynomials is even weaker. Fourth order polynomials is even weaker. As the weakness of, so this is a strong bias, this is a weaker bias. Very strong biases typically tend to have high test error. But then as you start weakening the hypothesis, bias of the hypothesis, it doesn't suddenly become the case that the test error will always reduce. It will sort of reduce up to some point and then starts increasing. And this is what explains whether we should be looking for higher order polynomials or lower order polynomials, or why we should avoid looking for, throw in 15 extra hidden variables and find a 17 level deep structure learned Bayes network for the data, and find that that doesn't work as well as the simple naive Bayes classifier because you overfit to the data. Okay? Okay? So, By the way, so I mean, this is just an example here for false positives and false negatives. You can look it up. So here is a hypothesis saying Russell waits only in Italian restaurants. If you take X10, Italian restaurant is yes, but he's not waiting. So this guy would have said he would wait, but you are actually, the hypothesis would have said you would wait, but it actually is not waiting, so it's a false positive. I'm just kind of, we talked about this example, but you can count the false positives and negatives. In Russell case, we assume probably false positives and false negatives are equal. They're both equal sized errors. In credit card transactions, it's one side. In the other case, the other example, which was the other example? Spam mail, it's the other side. It's the same thing, for example, for diseases, right? It's a complex trade-off, Should we tell somebody who doesn't have HIV AIDS that maybe they have HIV AIDS? Or should not tell somebody who does have? You see what I'm saying? What is the trade-off? False positives and false negatives, will have different trade-offs, and you basically use them as in the optimization metric to decide which is the best hypothesis. Okay? But the more important thing is also that you really are interested in reducing your error with respect to future, which is the test data. And training data is just a poor stand-in for the test data. Okay? So, what's a reasonable goal in designing a learning algorithm? We talked about all this. So what's a reasonable goal in designing a learning algorithm? When do you think that you've got a good learning algorithm? So the idea is that learner must classify all the test instances correctly, always. That's all a learner is supposed to do. So for example, if you all did my homework and that guy in the last call, or the guy who's looking at the laptop all the time and was mostly looking at Sen's old exams, winds up doing 100% in my exam. And he still gets his 100% because I gave a bad test and he did well. You see what I'm saying? So all that matters really is doing well on the test for a learner. That's what you're trying to do. Now, the test cases we assume are drawn from for you to have a hope of designing a learning algorithm, you assume that the test cases are drawn from the same distribution as the training cases. Okay? Now, it's not, and then of course the question is, should a learner always classify test examples correctly? Is a good learner always going to classify test examples correctly? Well, maybe training samples are not completely representative of the test samples, so a learner which learns from the training samples may still make errors with respect to the test samples. Nobody could have done better. And will you be able to always correctly identify? It's possible that the training data has noise. And so you will not be able to, you will miss some of the test data. So, in essence, while what you want in ideal case is a learner will always be able to correctly predict, the test data's class, what you really can hope for is to produce a probably, approximately correct hypothesis. You think I can get any more wishy-washy? Right? Probably, approximately correct. This is what you always wanted to say. Here is a solution, Rao, I think it's probably approximately correct. And I would say probably, approximately your grade is, something. And yet it's a technical point. Because learners cannot give guarantees. There's no way. It's from the get-go, there is no way of giving 100% guarantee. A sorting algorithm cannot say, I will give you a probably approximately sorted thing. And you'll say, no, I don't want this algorithm. But a learning algorithm will have to say it because it's about future and you don't know whether or not the future distribution is exactly the same as the training distribution. Okay? So the goal of the learner is to produce a probably approximately correct hypothesis for a given approximation or error rate epsilon and with the probability delta. Those are the two numbers. you want with probability less than or equal to delta, you make error at most epsilon. Error is the percentage of samples you misclassified. Okay? And a learner who misses one exam is not a bad learner. If they consistently do badly in the exam, then they are a bad learner. Okay? So this is telling you, okay, in any exam, with high probability, in most exams you will do better than 70%. That's what they say. So that I can give you, I'm a smart kid because I can give you 90% guarantee that in any exam you give me, I will do at least 70% or higher. That's what probably approximately correct means. Okay? So when is a learner A better than a learner B? Now, please indulge me by looking at each other and glare at the next person. He may or may not be a better learner than you. This is the question that we are doing here, right? Ultimately, who is the better learner is what we are doing. The whole entire school system that you've been forced to go through all your life is try to figure out who is a better learner. That's it. Okay? Who do you think is a better learner? How do you decide this? I mean, the answer is me. That's not a good answer. How do you decide this? So there is the question of, in some sense, when somebody says I'm a slow learner, what do they mean? They need more training examples. Okay? And then, of course, the teacher thinks maybe they need more homeworks and they give it to him. And then you say, you made my life miserable because I have to do more homework now. But really, you can't win both ways. But mostly when we say people are slow learners, they mean more examples to master a concept. The fast learners look at one example and master the concept. The slow learners will look at many examples and master the concept. Now here is the interesting thing. It's not as simple as that. There could be fast learners who have brain damage. And I don't mean it in any bad way. They could be, they had some disease and the brain is damaged. So what they learn very fast. Maybe your dog is an example. It has a brain, but believe me, it's never going to do quadratic equations. Unless you have a really nice dog. Okay? Okay, it learns what it learns pretty fast, but it doesn't learn quadratic equations. And then you have friends who learn quadratic equations, but don't do differentiation. And then you have you. And I don't want to go into details. What you cannot do. Right? So the interesting question then is I have this. There are learners which can learn very fast and then plateau. This is the percentage correct classification on the training data, on the test data. There are learners who can very quickly go like this. There are learners which can very slowly go like this. This is 1. This is 2. There are learners which very slowly go like that. 3. There are learners which very quickly go like this. 4. There are different types of algorithms. Okay, this, in terms of, if you decide on a level of performance that is minimal required, okay, let's say, so this is why, for example, people who are middle school science fair winners don't necessarily go on to get Nobel Prizes. And people who get Nobel Prizes, conversely, probably never went to a science fair. Okay, maybe they're slow, but when they learned the secrets of the universe. And then there are these eager kids who kind of learned very fast things and then plateaued after that. Okay, so you have all these kinds of learners. If you know how to design a good learning algorithm, this is the one. Very fast, barely, don't even show me any examples. I already know how to classify the test data. Right? And then a slow learner is like this, right? Basically, this one does finally reach the 100% but needs more examples. If I have limitations on my learning, so for example, I'm only looking for the best straight line separating the data. And it turns out that the true decision surface is a parabola. I will never find the 100% accuracy. I'll find just maximum I can reach would be the best line that comes close to that parabola. That's about it. In that case, essentially I would, because I'm learning straight lines, I will quickly learn the best straight line and plateau out. Remember this curve. When we compare, for example, decision tree learners to naive-Bayes classifiers to perceptrons, you will see curves like this. So the two issues in what is a good learning algorithm is how many samples does it need, and whether it reaches, and what is the asymptotic correctness it reaches. What I will do is assume, let's say, that my hypothesis space is expressive enough that the true hypothesis does exist there. That means I can reach 100% accuracy. Then the question is, among all the learning, so these are learning algorithms. This is learning algorithm 1, 2, 3, 4. Okay. Now, think of computational complexity. Do you talk about a complexity of a problem in terms of the algorithm you write for that problem? Or do you talk about it in terms of the problem itself? Problem itself. You say sorting is polynomial. Because even if you are very good at writing exponential time algorithm for it, somebody knows how to write a polynomial time algorithm. You say SAT is NP complete because till now nobody has been able to write an NP, a polynomial time algorithm. And if they were to write one for that, then a whole bunch of other hard problems also can be solved in polynomial time. So really, the complexity of the algorithm is different from complexity of the problem itself. So this is about complexity of the learning algorithm, individual learners. Complexity of the, so where you talk about learning curves. The complexity of the problem is given a specific problem, what is the best any learner can do? It may not be your learner, but what's the best any learner can do? In terms of the number of examples it needs to see to be able to differentiate, to be able to reach a hypothesis that is probably approximately correct with epsilon and delta as the probabilities. And it turns out that there's a very simple, this is actually, even though it looks dense and it's the end of the class and I'm not going to go through this, please look through this. It's very simple probability argument. And using that very simple probability argument, you can show that irrespective of the learning algorithm, irrespective of the problem, if the number of hypotheses that you are considering is h, then the number of samples you need to see to learn the concept with epsilon delta accuracy is greater than or equal to 1 over epsilon times log of 1 over delta plus log of h. This part you understand. You want less and less error, you need more and more examples. This part also you'll understand. You want more and more consistency, you need more and more examples. The interesting part is this. The difficulty of a learning problem depends on how many hypotheses are there for that problem that you are considering. If I were to give you logic data, propositional logic data, and you're looking for the best Boolean function, I told you the number of Boolean functions are 2 power 2 power n. Log of 2 power 2 power n is 2 power n. Because you are computer science people, you hear log, you assume it is with respect to base 2. Okay? Log of 2 power n is 2 power n. So learning an arbitrary Boolean function that is the best fit to the data you have requires exponential number of samples in the worst case. Okay? What if you don't feel like learning arbitrary Boolean functions? You just go ahead and make an assumption that the data in front of me can be written, the logical formula that I have can be written as a conjunction. It's a conjunctive formula. It's a conjunction like this, P and not Q and R and S. It could be a 4-size conjunction or 15-size conjunction or 100-size conjunction where 100 is the number of Boolean attributes. If I make that assumption, I'm biased now. I am looking not for Boolean functions, but for special class of Boolean functions, which are conjunctive functions. How many conjunctive Boolean functions are there? We already know that the number of Boolean functions are 2 power 2 power n. Conjunctive Boolean functions, if I have 100 variables, each variable can be in the formula positively, it can be in the formula negatively, or it can be missing from the formula. 3 possibilities for each variable. There are n variables. 3 power n. So instead of being 2 power n Boolean functions, now you are only considering a subset of Boolean functions that are only 3 power n size. If you take log of 3 power n, it's proportional to n. So learning conjunctive Boolean functions can be done with polynomial number of samples. Notice we don't talk about time in learning. We talk about number of samples. You said that because the difference between slow and fast learner is not in terms of the absolute time, but in terms of the number of examples. Conjunctive functions can be learned, in the worst case, with polynomial number of examples. Boolean functions, on the other hand, will require exponential number of examples. So that kind of gives you learning complexity of a problem as against just runtime complexity of a problem. I'll stop here. With this as the background, next time we look at decision tree learning and also decision surface learning.